Hello students, now I will tell you about the free oscillations and resonance. First I am taking the free oscillations. Free oscillations. When an oscillator oscillates with constant amplitude with constant amplitude. Such oscillations are called free oscillations. Free oscillations or natural oscillations. So this is like this. This is 0, this we have the x, this is we have the time t. Then I make this line. That like this. This is the constant amplitude A. This is the amplitude A. This is a plus A, this is a minus A. So you can see that this amplitude is constant. So here the body vibrates with its natural frequency. The frequency depends upon following factors. Number one, the material of oscillator. Number two, shape and size of oscillator. Third, the rigidity the rigidity of oscillator of material of the oscillator. Material means which kind of, to this one, suppose this is made of copper or brass or iron or your gold or silver, etc. There are so many materials are. Second, shape and size of the oscillator. If the shape you are given the different one, then the natural frequency will be different, and size depending upon when the oscillator is of his more size, then it will produce a very high sound. And the rigidity of the material, that how much it is a rigid. If it is rigid, very much rigidity is very high, then this will not vibrate. For example, you can see that the vibrations in the wood, paper, plastic cannot be created, or because of they are having the more rigidity and they absorb the energy very quickly. Because of that, the vibrations in them are very small. And if we take some material like your metals or your alloys, then the sound is very good. So they oscillate with the natural frequency. So this you can see that all the musical instruments like your guitar, violin, etc., and your drums also, they are having they always oscillate with the natural frequency. And you can see that if we have a stretched string, the natural frequency oscillations in stretched string. You can see that the frequency, this n equal to 1 upon 12 square root of t upon n. This is the natural frequency, where 12 is the length, L equal to length of string, T the tension force, and mass per unit length of string. Similarly, your organ pipes. So this m is equal to pi r square into rho. R the radius of the material, r radius of wire, and rho density of wire. So for different materials we have the different value of rho, the density, so we will have the different value of n. So thus the natural frequency depends upon all these factors for the stretched string. You can see that in guitar, sitar, and that we are having some other musical instruments. There are the wires stretched on some wooden frame, and they are tightened with the help of some screws, and then they produce the tension. So you can see that to produce a melodious sound, the material of the wire must be flexible, and that it could produce the vibrations. So the free oscillations always depend upon these things. So this is what about the free oscillations. Here we assume free oscillations take place when there is no damping force. Low damping force or the very low damping force. Only restoring force acts on the oscillator. So we can have, I told you that the natural frequency omega naught equal to square root of k upon n. So this is equal to 2 pi n equal to square root of k upon n, or n equal to 1 upon 2 pi square root of k upon n. This is our natural frequency. And in case of free oscillations, k is force constant, m the mass of oscillator, you are looking that I have taken the shape and size. So when we are taking the size, then we are taking the mass the same. The force F equal to minus kx. This is your m d2x upon dt square plus kx equal to 0. And this d2x upon dt square plus k upon a into x equal to 0. So this is d2x upon dt square plus omega naught square x equal to 0, where omega naught equal to square root of k upon a. This is what I have taken in here, the natural frequency. It is the differential equation for free vibrations. It is differential equation of free oscillations. So this is about the free oscillations, and after this I will tell you about the resonance. 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 It is a special kind of forced oscillations. Forced oscillations. When the frequency of periodic force acting on oscillator is equal to the natural frequency of oscillator the oscillator oscillates with increased amplitude because it absorbs more energy from the source. In this situation, an intense sound is produced. Because the amplitude increases, so the energy also increases. When the energy will increase, then definitely a intense sound will produce. And this phenomenon is called resonance. And its frequency is called resonance. Resonant frequency. So it is necessary that the frequency of the periodic force acting on the oscillator is equal to the natural frequency. Either it is equal or multiple of this one. Then there is the always the resonance. So in this case, the last sound, in intense sound, the intensity of the sound increases. So you can listen it, and we can also observe that the resonance is being taking place. For resonance, the required condition is that the frequency of periodic force must be equal or multiple of natural frequency of oscillator. Now we can see that when resonance takes place, if we neglect the damping of the medium, if damping is zero, the amplitude of oscillations will be infinity, and this can be shown as here. This is now, suppose we take now x, and this we take the frequency omega, then we can have the curve like this, that will goes to infinity. This is omega r, the natural frequency, and this is the resonant frequency. This is the natural frequency of the force in the amplitude. When only the starting force is acting there, then the amplitude will be so much, and when the damping is zero, then this will continue for infinity. For zero damping. In case when I told you about the force oscillations, there I told you the graphs. When there is frequency, the damping is very high, frequency is low, frequency very very low, and when when damping is very high, damping is low, damping very very low, when damping is zero. There I show you the four kinds of the curve. One of them was here, the last one, when the damping is zero. So the peaks goes to infinity, and in this case the natural this omega, the frequency is very high and very intense sound is produced in this case. Where omega equal to resonance frequency. And now I will take certain examples of resonance. On the radio. Radio. What happens in radio, that while we are tuning the radio, it means that we try to coincide the frequency of a radio set and that of some radio station. When the two frequencies are equal, you heard the sound, and all programs can be heard by this one. When frequency of LC circuit in radio is equal to the frequency of program broadcasted by radio station. The programs can be reset. Can be reset. If this is not so, then no program at all. You can see that when the soldiers are allowed to march past on the bridge over the river, then they are not allowed for the march past, because if the frequency of their feet is equal to the natural frequency of the bridge, then bridge will vibrate with more amplitude, so it may get damaged. Because of that, no march past is allowed on the bridge. Similarly, in your TV, you change the channels have the different frequencies. When the frequency of your TV set is equal to the frequency of some TV station, then you can listen or you can observe the programs. TV set. When frequency of TV set LC circuit is equal to some TV station TV set can be listened. So there are many examples of resonance that we have in our daily life. You can also see that certain engines or certain machines are not allowed to fix at the top of the house, because when the frequency of that machine is equal to the natural frequency of the house, then it may the resonance will take place, and as a result it may damage the house. So machines are not allowed on the top of the house. This is also the one of the case of resonance. So this is what about the resonance. So you all like, share and subscribe this video. Thank you.